He's gonna talk about one of their exciting designs and the design process associated with it. But before he gets started, just a little bit about the speaker. Dr. Krister has worked for new plants engineering in GE since 2008. He's the co-inventor of the design that he's going to speak about, and currently the manager of light water reactor technologies plant integration team. As a background, he has a PhD in nuclear engineering from University of Maryland, College Park, and worked as a senior reactor operator at Palisades nuclear plant in Michigan. Krister is initially from Sweden and currently resides very close to us in Wilmington, North Carolina. Krister, you have the floor.
Hello, how are you doing? Can you guys hear me okay?
Yep.
Great. I'm trying to make the screen look a little, I'm not used to Zoom, I guess. Okay, that looks good. Wow, there are a lot of people on here. Thanks everyone for joining this talk. Sorry I couldn't be there in person today. I had too many meetings. Can you see my screen too?
Yep.
Okay, and it's the right screen. It's the one that shows the BW300 innovative deployable SMR. Good. Okay, then I'll get started. Just first of all, I wanted to just remind everybody that GE Hitachi has a rich history of nuclear innovation, and we have basically been constantly designing or building nuclear plants since basically the 50s. And we've been working in nuclear since 1939 continuously. We have a GE Atomic or a GE Nuclear division since 1955, and over the years built 67 reactors in 10 different countries. And so we have successfully been able to take a US-based technology outside of the US and plants in Europe and Taiwan, Japan, Mexico, North America, and the US. Also boiling water reactors in Europe. But some of them we built and some of them were built by Siemens or Asea-Atom or ABB, which is now Westinghouse. But anyway, so we have a rich, basically rich history in nuclear, and we actually started out building very small reactors. Things like we were thinking we were going to fly reactors as airplanes and space and test reactors, reactors for universities. We've done a lot of small and lately a lot of big reactors. And here lately there's been a shift about since 2016, 17, we've shifted strategy from very, very large reactors down to smaller reactor types. You're probably familiar with this, but I don't know. It's a fission reactor. Boiling water reactors uses fission to boil water basically and send them through a once through heat cycle, Rankine cycle. Direct cycle, no secondary steam generator, traditional balance of plant for electricity generation. So it's just a turbine generator, condenser, feed water train. We used low enriched fuel, 3 to 5%. The water coolant is also used as a moderator, which slows down the fast neutron to the thermal spectrum. So it's has a better fission cross section. And finally, coolant is circulated through the core with natural circulation. So we use feed water pumps to get the feed water back into the core, into the vessel to replace the water coming out. But inside the vessel, there are no pumps circulating water. It's all done by natural circulation. Pretty simple reactor. It's once through. And if you look at the safety class or piping classes and safety classes of systems, we have a lot less pipe class 1 and safety class 1 equipment than a PWR would have or other active nuclear plants would have. The passive plants are very simple in that respect. Why is nuclear so exciting at the moment? And I wanted just to give you, this is kind of like, I'm not a economist or anything, but if you look at, for instance, this is MIT, and I'm sure you guys do similar modeling of different grids without dispatchable carbon-free power. So if you only have renewables, variable power sources on the grid versus if you have dispatchable power sources such as hydro or nuclear, your total system cost and electricity cost variation can be very high if you have a lot of variable power sources. So here is a modeling where there is no firm low carbon, which is water or nuclear. So you can see you can save a lot of system costs, and you can definitely dampen the variation of power prices spiking if you have more base load capability. And in Europe, it's becoming a problem with this. These variations are becoming a huge problem for both for people, of course, paying for electricity, but also for companies that rely on electricity for output of product. At the same time, you can see the carbon economy in Europe is actually in full swing. They're getting paid for or punished, or whatever you want to call it. They're getting fees for carbon that they release. And you can see certain countries are having a very hard time with their carbon footprint and paying a lot of money for it. So that actually gets pushed down to the customers. So the countries with more brown or black in them, in those countries, they're paying a lot more for their power. So you can see there's certain, like this is Estonia, this is Poland, the UK is yellow, Finland is yellow, which is interesting because they are a nuclear country, but they're building more nuclear actually in Finland. So you can see that France, that is a very large nuclear country, that's green. Sweden is green because of nuclear and hydro. And so Norway is also green because of hydro. They don't have any nuclear. But you can see that certain countries are definitely looking for a carbon-free footprint. Eventually, the hydrogen production is expected to take a big chunk or to increase quite a bit. And BWX300 is expected to provide a low-cost hydrogen production basis. So all these things are working together to drive up the interest for nuclear in the world, in Europe and in the US. You can also see that if you look, these are pretty nice. They're from the Lawrence Livermore National Laboratory, is that we want to try to electrify the energy transformation. So you can see that where, for instance, electricity generation can be actually used in more buckets than it is today in a much greater fashion. For instance, transportation is a great example where that little small orange line will probably become much thicker. And you can see that nuclear could be a big contributor to electrification of transportation. But at the same time, we also want to look for electrification for industrial use and commercial use and residential use. Another way to look at this to take over from natural gas and coal is to use nuclear and use the waste heat from nuclear to provide residential or commercial heat up, for instance, of district heating in Europe, not so much in the US. So there's definitely a push to have more nuclear in the world. So what is this BWX300? We've actually had a senior project with NC State students on the BWX300. It was a few years ago. I led a senior project on it. But the BWX300 is, the X stands for the 10th generation boiling water reactor. And it is 300 megawatt electric, about in that range. It leverages a previous design called the ESBWR, which was a US NRC licensed reactor, but it's smaller. We've scaled it down quite a bit. It still has world-class safety. We're using what we call a design to cost approach, where we set cost targets for the engineers, and engineers are aware of their status when it comes to cost for each system and piece and component that they're working on. So we try to keep costs from running away from us. We're trying to achieve a capital cost reduction per megawatt. It's capable of load following. It's really ideal for electricity generation, but it can also be used for industrial application, hydrogen production, and district heating. We've had a constructor on since basically very early in the project as a subcontractor. to help us with constructability reviews and making sure that we have a design that can actually be constructed in the field. And we don't have any showstoppers from the constructability. We've initiated licensing in both the US and in Canada. And our goal is to be operational by 2028. So how did we achieve the simplification? So if you look on the left, here's the ESBWR. And I'm not going to go over all the safety features of the ESBWR or all the features here. But if you look at it, you can see that there's a lot of water, the blue, a lot of pools, and a lot of piping. But it's really the gray that I'm looking for, the concrete. You can see that there's a lot of concrete needed to basically support the safety features of a BWR for ESBWR. And when we looked at previous projects, we spent actually several months looking at why can't we sell nuclear plants? Because in 2016, we were basically we didn't have any customers. We needed to rethink the way we do business. So we looked at our projects and why they had failed, and usually costs were too expensive, it took too long to build, and the customers basically, customers or energy policy or customer strategy changed because the projects were so such long duration and so expensive. But one thing we learned was that most of the cost of a nuclear plant is not connected to the metal and the pieces that we design. So the reactor vessel and the safety features, heat exchangers, and so on. It's related to how much money and labor and time it takes to put the concrete in the ground. So dig a hole and putting concrete in and making that work is really the reason construction projects take so long and get delays. So our goal from the beginning was to simplify the constructability and simplify the concrete structures of this plant. So we had, I guess, an idea that we wrote several patents on, which basically, and we also made the plant smaller. So we were able to basically change the safety case of the ESBWR by adding a few features, making it smaller. So we went from this relatively complex set of safety systems. And some of these had been actually added because we had made the ESBWR so large. So when we made it smaller, we were able to simplify the safety case down to just basically containment and containment isolation and reactor vessel isolation and this isolation condenser system. And we got basically, we have eliminated the suppression pool and the GDCS system from the design by making the plant very small and making the isolation function more strong. And so we were able to simplify and eliminate and downclass a lot of systems in the BWX300. But the overall goal, the simplification of the process systems wasn't really what saves you money. In fact, making a plant smaller makes the steel much more expensive because the way that it scales. However, if we were going after making sure we could fit this into a simple structure that can be built much faster than the ESBWR structure can be built. So we were going after basically a 50% building volume reduction per megawatt. So we were going to have more than 50% less concrete per megawatt. And since the plant is 20%, a fifth basically of the size of the ESBWR was 1500 megawatt electric output, and this one is 300 megawatt electric output. We have reduced the concrete volume by 90%. So if concrete volume drives schedule, we have reduced the schedule by 90%. So this takes a much shorter time to build than the ESBWR. That was the whole point. That was what was driving the simplification. That though, the BWX300 is really utilizing proven technology in the industry. If you look at so to speak, the complex part of the BWX300 is the reactor vessel, and all the components in the reactor vessel are either directly taken from a previous design or is an adaptation of a previous design that is simple, but all of it, as you can see, has been used before. So the fine motion control rods drives are the same as ABWR and ESBWR. The control rod blades are the same as the latest design for the BWR fleet, and we manage that design. We own the control rod, design product line, so we're using the latest version. We're using fuel that's already been delivered to 70% of the BWR fleet in the world, including non-GE BWR. So over almost 20,000 bundles have been in operation already. Chimney means we are just creating a steam space above the core to drive thermal driving head from the downcomer, so we get more flow in the core. The chimney is the same as ESBWR and Dodivard, but we're simplifying it. So we're having some experiments done to prove that simplification is working. And the reason we can simplify it is that we're using a smaller vessel. Steam separators are the same as basically the same as the BWR fleet, but improved for natural circulation. The steam dryer is the same as the ESBWR and same as the upgrades that we're putting in the current fleet. But the size is very near or identical to a plant in Switzerland that ran for many years. So we know this size vessel already. Finally, the reactor pressure vessel is done using traditional methods and the same way we've done pressure vessels before. And the diameters is the same size as a Swiss plant. Actually, the core geometry and the control rod geometry is the same as KKM. So we've already the core design is already proven as well. Proven components, prior testing, and operational history greatly accelerates the deployment schedule. So that was the whole idea behind it. And if you can look at this, key to simplicity is this isolation condenser. And here you can see kind of like a simplified diagram on how it works. When it's in operation, it takes steam from the reactor and it goes inside in this riser, and it goes on the inside of these heat exchanger tubes, which then boils the water on the outside. So these bubbles that are shown here, it's not the same steam. It's separated by a class 1 boundary, steel boundary, and then the condensate is returned to the vessel. So you're removing the K heat without actually removing inventory, which is a great feature of an isolation condenser. So we don't lose reactor water mass in the water coolant mass, but we can remove a lot of heat because we're using the latent heat of vaporization to remove the heat. So it's an extremely effective heat removal, and also in this case, pressure control system. What we did was we made the vessel and the plant 5 times smaller compared to the ESBWR, but we're actually using the ESBWR sized ICS. So it's relatively speaking 5 times larger than it was for the ESBWR. So it really helps the performance for this plant. We have 3 isolation condensers, but we really only need 1 to operate in order to accomplish the safety functions. So we're triple redundant. In addition to that, obviously, we have diverse actuation and a lot of other protections on the system, but that are not shown on this drawing. You can also see here that we've really tried to simplify the plants over time here. We started with a very simple little reactor called Valicitos BWR. And then we built more natural circulation plants, Humboldt Bay and Dodivard. But then we were pushed to make the plants much bigger. And we started using forced circulation. And the first forced circulation plants were very, very complex, as you can see, with steam generators and external pump piping like this, which you can imagine is, you could have a pipe break on this, any of these external loops. And, those plants are very complex compared to the current plant. Then we went to jet pumps and 2 external loops. Then we went to internal recirc pumps inside the vessel for the ABWR. Then the simplified boiling water reactor was a smaller vessel that was basically built from Dodivard. Then we went to ESBWR, which was too big to build. And now we're back to BWX 300. So it's kind of like 2 steps forward, 1 step back type of design approach. So now when we've gotten smaller again, we can go back to SBWR, Dodebard for design solutions that we may have abandoned in the past. So that's a lot of the work that we're doing here, is to try to resurrect our design history on the simple boiling water reactor side. I'm going to talk a little bit more details maybe about how we're using PRA and deterministic safety analysis to design this plant. From the very beginning, PRA team, probabilistic risk assessment team, and the design deterministic safety assessment team has been involved in this plant design from the very beginning. So first of all, we're designing this plant in accordance with defense lines. So we've basically instituted a design principle to follow these defense lines from the very start. So one thing that we did was we made a rule that so let me just go over these a little bit. Defense line 1 is basically saying this plant is designed with certain quality requirements in mind. It says conservatisms, margins, strengthens, and defense line 1 basically strengthens the subsequent defense lines. So this is mostly telling you how to design the plant, and so and what the rules are for each defense line in terms of quality requirements, redundancy requirements, diversity requirements, separation requirements, things like that, that you can basically set out rules for to make sure that the plant is going to be safe. Defense line 2 is basically your frontline systems. So in a boiling water reactor, that would be, let's say, reactor vessel level control. Reactor vessel level control is accomplished by, well, of course, you have to measure the level and you have to compare it to a target, which is usually dependent on power level. And then you would send that difference between the level and the target to a controller that would then control, in our case, feed water pump speed. So pump speeds up when the level is low and it speeds down when the level is high, based on that target error. That's a perfect defense line 2 system. So that system is basically a computer, and it interacts with 2 systems. So it's a frontline system, and it has support systems like an INC system. There's a feed water pump that pumps water into the RPV, and there's an INC system, and there's electric systems that power everything. And there's probably maybe a cooling system that makes sure the feed water pump doesn't overheat. And there's other support systems in that defense line. So that's a frontline system. That frontline system, it's available, and it can, so that if you have a perturbed level, this system can basically restore a level without help from any other system. So it can just basically adjust for sudden changes in level to a certain point. But at some point, if you completely, let's say you lose a pump, the pump trips, this frontline system cannot no longer support the level control anymore. So then you have a defense line behind it, basically defense line 3 will then look for, let's say the RPV, the reactor vessel level becomes really low because we lost the pumps in the feed water pump system. This system, completely separate from the support systems that are used in defense line 2, will then trip the reactor and isolate it on low reactor vessel level. So it's a completely separate system that does that. That is in completely separate sensors, actuators, everything is in a completely separate system, completely separate room, powered by a separate power supply, even using a separate technology. So different technology bases, it can't be the same INC system. So this independence is very important here between defense line 2 and 3, because this has to be independent of 2. Whatever failed 2 cannot propagate into defense line 3. Then as a backup to defense line 3, we have defense line 4. We call it 4 alpha, which is then a backup system. So if you have defense line 3 failures, okay, this tried to really trip the reactor, but it couldn't because it had a failure in it, let's say. then this defense line 4 alpha backs that up as a backup. So then we set a rule for plant level that 2 out of these 3 defense lines should be available for any event progression coming through here. So that means that defense line 3 has to be independent from 2 and 4 alpha. But we never count on 4 alpha to back up 2, so they can actually have the same support systems. In addition to that, we made defense line 3 passive and fail safe, which means that it has very few support systems. For instance, it doesn't need any AC power, it doesn't need any cooling water, it doesn't need any HVAC or anything like that to maintain its safety functions. So it becomes very easy to keep the independence between defense line 3 and the rest of the plant. And this is how you design a safe plant. In addition to that, we have a 5th defense line, which we call defense line 4 Bravo, which is kind of like severe accident systems in case, we have just this unexplained event that fails all this stuff. We still have a what if systems in defense line 4 Bravo that can take care of very, very rare extreme events, like extreme external events, or maybe some type of extreme common cause failure that takes out more than one of these frontline systems, or maybe both of support systems, though they are in 2 different buildings and 2 different manufacturers and so on. So we have that as well. And then defense line 5 is basically your management of, if you have a release, what do you do with public relations and making sure that people shelter in place and so on as needed. But this is basically defined in IEA guidelines, and we've designed the plant with this in mind from the very beginning. So it's important to think about when you think about nuclear plants that they're usually designed this way, with many, many defense lines in place to be safe. In addition to this, so this is defense in depth. Then we set up a safety analysis framework where the hazards evaluations that I talked about, these different faults can be from fires or floods or internal missiles or just internal random failures. We do what we call, we create what we call a fault list, which basically lists all the different postulated events. And we do deterministic safety analysis on the fault list. But at the same time, we also do probabilistic safety analysis. And the probabilistic safety analysis is also done with these defense lines in mind. So they know in their event trees what defense lines each thing that we're crediting in the PRA is, as well as the deterministic safety analysis also keeps these defense lines in mind when they do their work. And then we have these, of course, so we set up some fault lists. We know what we're doing because we know BWRs pretty well. We evaluate failure modes. We come up with limiting cases. We categorize events based on frequency. And we do deterministic and probabilistic safety analysis to validate plant responses. But then we have these feedback loops where, deterministic safety analysis might find the case where, we need to look at this other case that we didn't think about ahead of time. But the same thing with probabilistic safety assessment, that usually finds relationships between systems that we hadn't considered when we looked at them, on face value. Like, for instance, a fire in a turbine building can take out a weird system that we didn't even consider as part of the design, but they come up with other relationships. So they have this feedback loop to the fault list where we basically get the feedback loop both from PRA and the deterministic safety assessment, but also this fault list centers everybody around the same plant. So what's happened in the past, in GE at least, probabilistic safety assessment and deterministic safety assessment have been kind of lived in their own little worlds and not combined, haven't cooperated as well. So this helps keeping everybody on the same page, especially when it comes to these very, very rare extreme events like I talked about. It's very good to have both deterministic and probabilistic safety assessment together working on the same thing. If you look at the isolation condenser system and how we treat it, it's basically a category C passive safety system based on IEA. It operates without power or external cooling. The condensate return line opens on signal or low or loss of power. It's not low of power, sorry. steam generator and RPV and condensation in the elevator heat exchangers drives flow through the system. So you can kind of see how we did that. It's 3 by 100. So each of these heat exchangers is 100% capacity for decay heat removal and overpressure protection. We have mechanically diverse valves on the return lines, and the instrumentation and controls is fail safe and with multiple redundant and diverse INC platforms. So it's like a multi-layered passive cooling system which achieves the same required safety functions as traditional boiling water reactor emergency core cooling system, but with much greater reliability. And I would also add, without any alternating current. We don't need any power supply to keep this design feature in place and keep the decay heat removal going. I think this is gonna play. So normal operation, you can see that the steam, which is the yellow, is going towards the turbine through this main steam lines. And you can see that the feed water is coming back into the vessel in the blue lines. That's normal. So what happens then during a turbine trip or a main steam line isolation event? It's going to be a mild transient because we have a very, very large steam volume. But you can imagine that if you suddenly stop flow on a steam line, there'll be a pressure transient. In normal BWRs, or existing BWRs, maybe I should say, usually that results in a pressure transient, which opens safety relief valves. And when the safety relief valves open, they relieve inventory, basically mass of water, into a suppression pool in the containment. And then you use a pump to pump that water back into the vessel to maintain water level. But in this plant, since the response is very mild, we don't have safety relief valves. We have designed the plant to not need safety relief valves. And so there is no need to replenish or pump back in water in order to maintain the inventory. Instead, we use the isolation condenser to remove heat, and it retains the inventory, right? Because it just circulates steam and returns water, and we don't have to pump in water. So this is a huge simplification compared to existing boiling water reactors. Try to shift here. So you can see that the normal configuration of the ICS is to have open valves, and but the return valve is closed. Here, the supply valve is open, but the return valve is closed. So all that has to happen for the ICS isolation condenser system to get into service is to open these valves, and you'll establish a flow circulation loop through the isolation condenser heat exchanger. We do have a 7-day coping time for design basis accident, which includes station blackouts and loca and so on, small break loca. We have simple action after 7 days to increase time to much, much longer than 7 days. So let's look at what happens when you have a turbine trip. Then the return valve will open, and then you have steam flow going up to the isolation condenser, and then condensate water going back into the vessel. So you're basically, I'll play that again. You can see that the valves close on the reactor vessel, and then the isolation valves open. Actually, they fail open. Also, they fail safe, and the isolation condenser system is in service. And then you start, after a while, you start boiling the water and react in the isolation condenser pool. But I had another page in here. So that's how the safety case kind of works for the boiling water reactor BWX300. Now I'm going to just talk a little bit more about project implementation and what we're doing on the constructability side. So this is the page that I was supposed to have first. I'm sorry, it ended up in the wrong place. So simplified construction, I'll start here and then I'll go here. You can see that we have constructability and design to cost in mind, and I'm going to explain why. So we're using a cylindrical building one key aspect of this is that this building in the middle here is the only safety class 1 building, seismic category 1 building in the whole plant. And this is a cylindrical building because that gives us the most strength for this building. And a cylinder is the strongest building instead of a square. And it's sitting basically 2/3 in the ground. And we're using underground construction methods used in other industries, such as tunnel boring and so on. So we use a minimum excavation method. Maximum use of catalog items because the plant is small. So we don't have to build the biggest, turbine ever, biggest feed water pump ever. That type of equipment, especially on the BOP, we're taking basically building blocks that have already been used in the 300 megawatt class natural gas and coal plants, and which there are a lot of those plants already. For instance, the turbine generator package is from a standard combined natural gas plant, but with some modifications for nuclear. Here's the control building, and here's the reactor building, and this is the turbine building. The other thing you see, we don't have, the turbine building is not underground, it's sitting on ground, so we have minimized excavation, both for the control building and the turbine building. In addition to that, we're using something called steel bricks, which is a modular approach to putting the building together, the reactor building together. Actually, we're probably going to use this for all buildings. You can see that it's an adaptable way of doing modular construction based on how big of a piece you can bring to site. So you can make these small if you need them, or you can make them really big if you need them to be, depending on the site and how close it is to, let's say, a barge port with a barge, or if you have to truck in things on a car, on a truck. So it depends. That will basically dictate the sizes of these modular pieces. Basically, it's similar to a Lego kit. You can use the Lego pieces, you can put them together before you put them into the big model, or you can basically ship them in individually. We're going to use vertical shaft boring. We basically use a vertical shaft boring, then we do a circular slurry, and you basically do minimum excavation. You don't do what we call bathtub excavation, and we eliminate a 1 million cubic yard of excavation and engineering backfill compared to traditional methods. And I don't know if you have thought about this, but moving dirt around is usually the most time-consuming thing in a construction project. I mean, I know when I drive into Raleigh and you have all those road construction projects, and they're all moving dirt around, truck by truck, and they have to move just, probably millions of cubic yards of dirt, and it takes a long time because you have to move them truck by truck, and a truck takes about 10 to 20 cubic yards of dirt. So it's like a lot of trucks. So if you can eliminate excavation, you basically can shorten the time schedule of a project a great amount. At the same time, we're then also leveraging our capabilities for GEH reactor technology, because we are doing outages. We're doing service work all over the world. We have a mock-up facility in California where we actually have a real mock-up of a refueling outage area where we can practice, fuel moves with dummy bundles. We can practice disassembly and reassembly of a vessel, and you can basically use it for tours, but also for qualification. We use it for qualification of refueling area workers. You can also practice installing modifications and tooling, and we also practice our in-vessel visual inspection and craft here as well, because we have real indications that you have to basically get to in this pool that you can practice on your IVVI tools, which is a very, very important part of an outage. So this basically this world-class training leads to that we're like best-in-class services in the world when it comes to servicing boiling water reactors. And we also use 3D we have been using 3D in the design of this plant from the very start. We started in 2D, but it became too complicated and hard to manage. So we have moved into a 3D design from the very beginning. So we use that 3D capability to then transfer it over to virtual reality. So you can do, well, it's a great demonstration tool, but it's also really handy for walkdowns and so on. And finally, we are basically located all over the world. Not all over the world. There are certain places we're not in, but we are definitely represented in many countries in the world. And so that was the last slide I had, except, yeah, we want to try to do, of course, with this plant, we want to try to build a fleet of plant and then start out basically having a fleet, basically mindset. So one thing with the current fleet of BWRs is that they're all very similar. No, they're all very different from each other. We've allowed them to be different. And we've allowed, even on one site, the plants can be completely different. And the intention here is to keep more of a fleet mentality in mind for the BWX300. I think that's it. And this is the last picture of my presentation, but also a very fancy version of the BWX300. Do you guys have any questions?
Thank you very much. We have one question in chat, and while I do this, be ready for questions as well. Mustafa is asking, how will you deal with the heat exchanger tube rupture and the isolation condenser system?
Yeah, that is a postulated initiating event, and we have isolation valves on each isolation condenser that will isolate on an indication of a leak. And we have several indications of that leak that feeds those isolation valves.
And how would you detect such an event before a release?
We're working on several ways of detecting that right now with both flow differential meters and elbow taps, and also we will use radiation detection in the compartment that the heat exchanger is sitting in.
All right, thank you. Another one for Mustafa. How many modules per plant are you considering, and how many operators?
The modules, it depends on the plant, so at the specific location. I can't really answer that. It really depends on the transportation plan. And it's different for each project that we're working on right now. And when it comes to operating staff, it'll be staffed very similar to, when it comes to operators, it'll be a staff. The minimum complement in the control room is, I think we want to go for about 3 people, but we'll have 5 or 6 shifts. But we still need about 5 to 6 people per shift.
Sounds
depends
good.
on the site also, depends on how many units we have. There's some of those that can be combined for several units, and there's some of those that have to be dedicated to a control room.
Thank you. Another one from Rob. When are you going to do another senior design project with us?
Yeah, I guess we can sign up for that. I'm not really, I haven't been involved in the senior design project selection, as in I haven't been asked to provide any more cool ideas, but I will try to look out for that next time around when it's next year or this fall. I'll look for that this fall. Definitely.
Yep, let's talk during the summer. All right, another one from Ed. How does GE Hitachi address common cause failures in digital INC systems? If a diverse actuation system is implemented, do you think having a DAS system is an economically efficient alternative? Or does the NRC need to change the regulatory perspective on defense in depth for digital systems?
I think NRC needs to change, but how we took care of it was basically through this defense in depth. It's proven we started this without, well, we started this knowing that when we started this plant work, we had no US customers whatsoever. So we actually ignored the US rules and we went straight to IEA and outside of US because we thought that was where the market was. And I think US is going to have to adapt a little bit to be more like the rest of the world. That's my personal opinion. It's probably not. If you ask GE, they might have a different opinion, but that's what I think. And but I think this defense in depth scheme actually works when you look at if we have complete independence between the support systems in different defense lines. This provides very good protection, and you can see that in our PRA numbers, which are very, very low.
Do you have any slide on the PRA numbers?
I don't have any final PRA numbers to present.
Okay.
We're working on it, but it's going to be very low. That's all I can say. Yeah.
All right. Luke, please go ahead.
Yes, hi. I'm a PRA engineer. I'd first like to say I'm impressed with your consideration of diversity and separation in the layers of defense and depth. I think that's often something that's lacking in existing designs. I did see you have a goal of the EPZ at the site boundary. That's an ambitious goal, especially with the US NRC. I'm wondering whether, I mean, it's a risk-based goal. So you can either address it from the frequency, either arguing that it's so unlikely you would get the kind of large release that would require an EPZ, or you can say that, well, the dose wouldn't be that bad. Knowing that you're a BWR, do you have already postulated doses if you were to get the kind of catastrophic accident that would both cause core damage and failure containment?
So what we've done is, it's a little bit interesting because we're working on, actually, to achieve this goal. This has been an aspirational goal, as you may understand. So that's been what I call a stretch goal for us to achieve goal APC at site boundary. Since we are a light water reactor, we know that it's going to be harder for us than it is for maybe other reactor types. But what we have done is basically, we're at the point where we are limiting postulated event for EPC dose is reactor vessel rupture. And if you think about reactor vessel rupture, it's at least for our reactor vessel, we estimate it to be very, very low frequency. In that sense, so if you look at frequency argument, and your postulated initial event is that the reactor vessel breaks, it's going to be about 10 to the minus 8 or 10 to the minus 9. So it's very low frequency. So we're getting very close to that goal in my mind. So our reference source term for EPC is not going to be RPV rupture because we're going to basically, it's beyond design basis or residual risk almost. So we have to come up with a representative source term. You cannot achieve this goal using the US framework that is in place today, if you read the reg docs today. But actually, even the NRC is moving in the direction of not having the postulated dose being done the way that it's done in the reg guides today is extremely conservative for a plant like BWX300.
Yes, I absolutely agree with that it's conservative. A quick observation, the 10 to minus 8 numbers, make sure you specify that it applies to random internal events. I've got some bad news about extreme external hazards.
Yes, I know seismic events come and ruin it for us.
Yes, I've been through this. It's going to be a problem. You'll get severe diminishing returns with your defensive depths.
But we have, for seismic events, we also have, we have worked on the fragilities for all of our key systems for seismic to get to where we need to be for seismic events in the same ballpark.
Do you have a safe shutdown earthquake already defined?
We do, but I don't know all the details, but we have worked on the seismic PRA quite a bit because that's been hard. Like you said, it's very hard. It's very hard to do, and it's very hard. You need to, the uncertainties take over and become the dominating impact. The uncertainty of a large earthquake it's not a problem, but it needs to be accounted for in the design, and that's what we're working on right now.
Thank you.
All right, thank you, Luke.
Thank you.
Glenn, please go ahead.
Yeah, thank you. My name is Glenn Lawson. Full disclosure, I'm a PRA engineer at X Energy. So I really appreciate your presentation here. I learned a lot, and I think one of your slides already answered the question I was going to ask you. Is the mission time. We're trying to find a fair mission time for the PRA, And I think your slide here says that you're applying a 7-day coping time to all accidents. So all your initiators will have to run through a 7-day mission time. Is that correct?
That's correct. But we are setting some rules on the 7-day coping time because, like an SBO, 7-day SBO is not just a regular old SBO. It's a little bit less, especially if you're right next to, let's say, 4 reactors. You're going to have a low frequency event that starts, that's going to last for 7 days. You know, if you know what I mean.
Yeah.
So we are setting some design rules around it, but our goal, actually, if everything works as it should, this plant should have a 16-day coping time.
Okay. Wow. Okay. That's impressive. Okay. And I have lots of questions. I'll just ask one more question. That the next slide for safety analysis framework, when you talk about the centralized fault list, are you referring to essentially your event sequences, that you essentially get all your event sequences listed and then the company works on that same list? Is that what you mean by the fault list?
Yeah, pretty much. It has a lot more than that, but that is the basis for it. Yeah.
Okay. All right, great. Well, thank you very much.
It just basically, it's an agreed upon list of postulated initiating events. Yeah. Based on our hazards, based on our probabilistic safety, based on our fault evaluation and deterministic safety assessments.
Okay.
So you put internal, external, everything in there,
Okay.
and drive
Awesome.
the work. Yeah.
All right, great.
So,
Thank you.
to piggyback on Glenn's question on the fault evaluations, so if you bookkeep a list of initiating events, what is going to be the interface to the system engineers?
Very good question. And it depends, since this is a public record, we have a way to pass along functional requirements and performance requirements to the systems from there.
Mhm. Okay. Is that the systems engineering approach?
Like that's what I do. That's what we do in our group, is coming up with a scheme we coordinate this fault list, even though everybody around us are different groups. And then we pass along the plant level requirements down to system level. That's why our group exists.
Sounds good. All right, another one from Ed. What is the major difference between the IEA requirements for digital instrumentation and control systems and the NRC requirements?
I think the NRC requirements are written for, what should you call it? They're way too old school, and they have not taken IEC requirements and codes and standards into account, and they're way too like ad hoc. They're not really thinking about this as far as using a defense line approach. They're more thinking individual system and back up to individual systems and looking at it from a high level plant level like this. That's what I think is the difference.
All right. Another question also from chat. Given the expected need for NRC changes to accommodate the reactors, do any of the expected customers have the political lobbying networks necessary for such changes, or is it mostly a hopeful idea rather than a planned course of action?
It's a planned course of action. We do licensed topical reports on key items. We've already submitted, I think, 6, and we've gotten them approved. We've waited to do the defense lines and the INC because we have had no current customers in the US, so there hasn't been really that much push for it. But it's coming. So we have, if you look on the docket, you can look in Adams, you can find several licensing topical reports for BWRX 300 on there.
Any questions from the audience here?
I'm just wondering what tool does they use for the PRA? Do they have their own tool, or they depend on CAFTA, another tool from investment?
What PRA solvers are you using? Are you using CAFTA or other tools?
Yeah, we're using standard EPRI tools, tool suite, WinMax, and yeah, CAFTA. Yep, and we're following the ASME standard.
Any other questions?
Did I say ASME? I probably meant ANS. Anyway, the US standards.
ANS is semi-standard, PRA standard. Yeah. All right. One last time. Any more questions? If you're in chat, submit your question. All right, let's thank the speaker one more time. Thank you for attending our seminar. If you have
very
any more
much.
questions for Kristen, let us know and I'll pass on the information to him. Thank you very
Thank
much.
you very much, everyone. I promise I will do a senior project, or one of my guys will do a senior.
Sounds good.
And I appreciate the opportunity to talk to all of you, and have a good day.
You too. Thank you. Bye-bye.